Good evening. On behalf of the ISU Space Society, I'd like to welcome everybody and thank everybody for showing up this evening. I'd like to give you a little background on our speaker tonight. It's Mr. Brian O'Connor. Brian O'Connor is the chairman of NASA's Flight Safety Panel and was pilot of the Space Shuttle Atlantis, logging 165 hours in space. During the mission, the crew deployed 3 communications satellites and conducted 2 spacewalks to demonstrate space station construction techniques. He received his master's in aeronautical systems from the University of West Florida and is a graduate of the Naval Academy. And as of recent, he has been named to command the Space Lab shuttle flight in June of 1990. I'd like you all to give a warm welcome to Mr. Brian O'Connor.
Thank you very much. I'd like to thank Andy McGuire and his fellow officers of the Society, Mark Grethen and Paul Harderson, and also to Pat Miller, who's the lectures program coordinator who helped get me here today. All these people took their own time, and the students of those took a lot of time out of what I guess you call the crunch, or that period of time when you're trying to get ready for finals and final projects and senior projects and so on. I also appreciate the fact that so many of you here showed up tonight to hear a little bit about the manned space program, because I know you're all trying to get ready for tests and so on. But if you'll bear with me, I would like to bring you a little bit up to date on your space program, especially your manned space program. Last week we had the flight readiness review for our next mission, which is scheduled to go on the 28th of April. This will be the 4th mission since the accident of Challenger. And truly we feel in Houston that we're really back in the manned space program again. You know, I think we were the same as everybody here when the Discovery went up for STS-26, holding our breath at least through the time when those solid rocket boosters fell off. I was telling some of the guys that the astronaut office has always tended to be that way. But I think the whole public is that way now. People who used to cheer when they saw the shuttle lift off the launch pad now kind of hold off a little bit until they see those rockets fall off. I want to tell you a little bit about that recovery period. It took 2 3/4 years to go from the Challenger accident until STS-26, the return to spaceflight. That's a long time, but we're talking about an incredibly complicated piece of machinery in the space shuttle. Now, you all who are working in engineering fields and especially the aeronautical engineering side of the house probably have been exposed to the fact that they don't build aircraft and spacecraft like they used to back in World War II, where they would go from drawing board to dropping bombs on the Nazis in only 90 days. Those days of building aircraft and aircraft systems that quickly and certifying them for safe flight are gone. They're long gone. We had a choice after the Challenger accident. We could have, when we realized what the problem was, and by the way, we found that out fairly quickly. We found out what the problem was on the Challenger accident as far as the design of the solid rocket boosters go within weeks of the accident. We had some people who suspected it right away, and as we pulled the pieces out of the water and we looked at the films, and especially on the films, we realized that there was a gross design problem with the solid rocket booster. And before Dr. Feynman on the commission did his little demonstration with the cold water and the O-ring, people at NASA and the contractors knew that we had a cold weather problem, we had a design problem, and an environmental problem. The people who worked the design and the people who knew the environment hadn't talked to each other well enough before that launch. In fact, before the first launch of the shuttle. It was a breakthrough not only in the design area. We had a piece of equipment break on us, but it was a fault of the whole management scheme, the whole way we were doing business at NASA. And that is part of the reason why it took so long to come back around. We had a new design on the drawing board and ready to go to print and ready for new metal parts and new forgings within a couple of months after the accident, and we were testing prototypes of the new design by the next summer after the accident, within 6 months. But why did it take 2 3/4 years before we could fly the shuttle again? The main reason for that is that today, when you build or you modify in a large way a big complicated piece of equipment like the shuttle, the redesign and the bending of the metal turns out to be a small portion of the time that it takes to get it operational again. What really took a long time was the testing and the verification and the certification of that thing. When you look at the test matrix to certify that that piece of equipment was going to be safe and ready to fly, it took up a whole page. There were a lot of subscale tests. We had scale model tests that we had to do. We had full-scale tests, but on only one segment, or in some cases only 2 segments of the whole rocket. We had to fire those things over and over again in different corners of the envelope. We had to do them at different temperatures. We had to basically recertify what we had already done to those rockets before the very first shuttle flight, but we had to go through that whole scenario again. And we actually did it. We did more tests in a shorter amount of time during this turnaround time than we had before the first shuttle flight. But it's the testing that takes so long these days to get things on a complicated piece of equipment like the shuttle. We have another thing on the drawing boards right now, a drag chute. Many of you probably noticed that when the Russians landed their space shuttle, they had I think it was 3 small dragster type drag chutes that came out the back. Those people don't have as much trouble getting things operational as we do. It doesn't take them as long a time. We also have a drag chute on the drawing boards. We've known we needed one for quite a while, but we still can't get that thing on there and tested and certified for another 3 years. Right now we're still in the testing phase of simulator testing phase, where we're doing 6 degree of freedom simulations out at Ames Research Center to certify how long the shroud line has to be, how big the chute has to be in order to ensure satisfactory handling qualities when that chute comes out. It doesn't pull the nose back up in the air and so on. But it's the testing that gets you. And those of you who go into aerospace industry, I think you're going to find that you'll be immersed in that same problem. You're not going to just be people who are designing things and then next week come out and watch your product enter the fleet, fly into space, get into the payload bay, or whatever. You're going to be tied up with post-design test work for a long time. And so it's test engineering that needs some emphasis. And in fact, there are some people who totally make their living. Aeronautical engineers from this room here may find themselves as flight test engineers, where all you will do is flight test on aircraft or flight test on rocket type machinery. That's why it took so long to get where we are today. But now we're back in space, and the question now becomes, what happens the next time we see something that goes wrong? Can we recover any quicker? Are we any better off today than we were then? Well, it turns out that while we were redesigning that solid rocket booster, we kind of took advantage of the American public in a way. And I'm not apologizing for it because I think it's great the way we did it. The Congress came to us and said, NASA, you're down, you need to get back up again, what do you need? And we told them what we needed, and they funded every penny of it. And what we needed was not just to get the solid rocket booster fixed, but we had over 300 fixes that came out on the table after that accident. We had a great big house cleaning, in effect. Just about every person who had a subsystem problem that he'd been carrying along with him for years, everyone who had a safety concern about a design or a marginal factor of safety or a hazard that had residual risk left over with it, all those things came out on the table. We had big debates about how to prioritize those things, which of those we really needed to fix while we were down, and so on. And the way it worked out is that we knew that it would take a long time to certify the new solid rocket booster for flight. And while that downtime was in progress, was there anything else we could do to make the shuttle better and safer? And those 300 things came out on the table. Some of those 300 were not on the flight vehicle. Some of them were with the ground equipment, the ground support equipment down at the Cape. launch pad, and so on. But there were over 200 fixes that went into the orbiter itself. And Congress gladly paid every penny of every bit of that. Now we're back in our penny pinching mode again, and we have to argue for every possible modification, whether it be safety, performance, or whatever. But during that downtime, we had sort of a grace period where we were able to get into the kind of mode we used to be back in the Apollo days when money didn't seem to be a factor. There was another thing that went on, though. We weren't just fixing equipment during the downtime. We were fixing the way we do business at NASA. We had a safety program, for example, at NASA that was pretty bad. There's a lot of talk about how you need, in order to have a good product, you need to have a system safety effort that goes alongside of it and asks those questions about hazards and failure modes and so on. The what ifs. What if this fails? What will happen? Should we fix that? That sort of dialogue needs to go along with any design. And there may be some of you in here that find yourself as system safety experts after you've gotten out of this environment here and you get into aerospace industry. You're going to find that there's some big openings in that area. NASA has turned around how it views system safety. We had safety people at NASA and in the contractors who had been stuck in that job because the contract says there will be a safety officer or there will be a safety program. Those people had been stuck in those jobs for years, and it turns out that in order to have a good safety program, you have to have people rotating in and out of that kind of a job, because safety people are the kind that come in and they don't have good news. They always come in and make life difficult for not only the designer but also the operator. And you can only put up with that sort of thing for a couple of years, maybe 3 or 4 years before you burn out. So safety is a discipline that needs to have fresh people coming in all the time. And you get the most out of them, and then you send them back to design and engineering and flight test and operations. And they've got a good outlook on life when they go back to there, because they have now looked at it from the safety viewpoint. They take that viewpoint back with them, but you don't let them fester there, and you don't let them get old and crusty and let the point on their spear get dull. And that's what had happened at NASA. We had people in the safety organizations who had been there in the same jobs for 20 years, and they had totally lost all their credibility. They really didn't know what was going on anymore. They were just going through the paces. And we really had a very poor safety program. The independent safety people that were supposed to be doing the job of making sure that things didn't fall through the crack had fallen through the crack themselves years ago. I think you'll find right now at NASA that it's a totally different outlook. We've got good people in safety, people that were at the top of the heap in operations and engineering have now been transferred to safety, and they're finding that they enjoy it. Safety is one of those areas where anything's fair game. You can go and you can ping on any part of any aspect of the operation or the design engineer's world, and be useful to the program. And that's what we're looking for, is people that are interested in that sort of thing, that have a system engineering outlook on life. And NASA promises, and the contractors are promising now, that they will do that for long term. We've seen that we do have to have that independent bunch to help us with our designs and make sure these problems don't show up again. So I say that because this is kind of new. And there may be some people in here that don't know anything about system safety, never even heard of it. But if you go to work for a contractor that works for the military, especially, or for NASA, I think you'll find that there's going to be a big call for credible, well-educated, systems engineering background safety people who can help us get the job done. That's one of the other big changes that we made at NASA. And one other word on changes that we made after the accident, and that was risk management. Risk management turned out to be an elusive subject. It basically is managing a project that has risk to it, and the decision-making process that you go through day after day in deciding which kind of modifications to put in and when, whether something ought to be changed, what kind of operation we're doing and should we change that. And we spent a lot of time working on how to manage risks in the program in view of the fact that the space shuttle is quite a bit different from the Apollo and the Gemini and the Skylab projects. The space shuttle flies and then it comes back and we have to get it ready to fly again. And we found that we are in a different mode than we used to be at NASA. We're making decisions about things that ought to be done between flights. The vehicles will get old after a while. People will find cracks in them when they come back. Should we fly it again or should we fix it? These kind of decisions we never had to make before. We're finding that we're making the same sort of decisions as people who fly airlines and people who fly combat aircraft. And those kind of trade-offs that they go through in managing and maintaining those vehicles between flights. So that's another area that's received a lot of attention. A lot of high-powered thinking has gone on in that area. And we have found that the safety people that we have hired and nurtured here this last few years to get them to a point where they can be useful to us are also being very useful in this risk management area. We're finding that we can ask those folks to help us with those questions and act as not only just auditors of what we're doing, but also advisors. And so the whole thing kind of tends to be a big reawakening for NASA on how to do business. Now, that's a little recent history, I guess. But what I'd like to do now is get you back to the space shuttle. I had the tremendous privilege in 1985 of being allowed to fly on the shuttle Atlantis. And we had a 7-day mission. We deployed some satellites. We had 2 fellows on board that did a spacewalk. Dr. Mary Cleve waved them around on the end of the arm for a while and did some science. And all in all, we did a few things for our country, and we had a good time while we were at it. I'd like to refresh you on what the space shuttle is all about. And in order to do that, we in the astronaut office have made a movie that takes a bunch of little clips from various space missions, not just the one I was on, but various missions, to show you some of the things that can be done and have been done with the space shuttle, why it's a unique vehicle and will be unique for a long time. And it also shows another side, and that is what's it like living on board? What's it like to be in weightlessness? The living accommodations, how you eat and sleep and so on up there. A little bit of that is in here too, because we always tend to get a lot of questions about that side of it. You should be aware that as the space shuttle continues to fly now, we're kind of getting out of the commercialized side of the house. You will notice in this movie that I show that we were getting pretty heavy into deploying commercial communication satellites and television satellites. NASA, as part of the relook after the accident, has decided to go back to expendable launch boosters to do some of those things that can be done by other vehicles, and to spend a little more time working on scientific missions with the shuttle, because that's where the human being in space is really key and unique. And I think the next bunch of missions that you see coming up are going to be those that are uniquely suitable to the shuttle. But I'll go ahead and talk a little bit about some of those satellites that we did deploy on earlier missions. If I can have the lights turned down, and we'll start the projector. Okay, this was a 5-person crew, but these guys turned on the camera to kind of fool around with the capsule communicator down in Houston to make it look like 6. This is the shuttle on the liftoff. Does that look a little jumpy to you? Well, it feels real jumpy on launch, I'll tell you that. When those 2 solid rocket boosters fire, you know you're headed someplace. It's like somebody came up from behind you and hit the back of your seat with a 4x4. It's not quite like those earlier attempts. And it's amazing to think that it was just 40, 50 years ago these people were doing these things. This is the first rocket pilot right here. And then here we were in Skylab day in the mid-70s, Al Bean doing some somersaults in the big Skylab. And just 25 years ago, we had Alan Shepard launch for 15 minutes, suborbital, but it was the first American in space in that little Mercury space capsule on top of that redstone. And then just within 10 years of that, we had the biggest space vehicle ever to take people in space, Saturn V, take 3 people to the moon. Now here's a shot of John Young, who is still an active astronaut down in Houston. And here he is driving the lunar rover. And there's another shot of John walking across the moon's surface. He told me that when he came back into the Apollo, the lunar ascent vehicle after that moonwalk, that he had a sneezing fit because he got dust in his nose when he took his suit off. And he's the only guy I know that ever had moon dust in his nose. Here's a typical space shuttle launch. You lift off, you've got about 5.5 million pounds of thrust. That flame's about 700 feet long underneath you. And when you roll over, you're rolling to the launch azimuth. Most of the launches are 28 degrees because that's the latitude of Cape Canaveral. And this is what it looks like out the pilot's window. You're upside down now, so you're going from upper right to lower left. And you can see as you go through the atmosphere how it changes in color. The day sky is black up there. You can't see the stars in the daytime. You only see them on the night side of the Earth. But it is black. And this is a shot of the shuttle taken from a little satellite that was deployed out of the shuttle on STS-7. Now we take you inside the cabin and then get a little idea there with Roy Bridges floating around of the weightlessness. Here we see Bob Crippen and his crew coming down for pictures. And it's kind of neat to be able to just go head first down from the top floor to the lower floor. But not everything about weightlessness is neat. Paper is a real problem up there. Just trying to fold it or scroll it or roll it up in a ball is not that easy. And so waste management is a big issue up there. This is one of those communication satellites I told you about. Typically, we deploy those at about 150 to 200 miles up. And then they have their own motor that takes them up to 22,000 mile orbit where they're geostationary. We have a couple of different modes. They all tend to be spin stabilized. This is the Frisbee mode here that we use with the SYNCOM satellites. That's quite a lot bigger satellite than the other type, the Hughes satellite. This is an RCA television satellite. The mission I was on, we had one of these and 2 of the Hughes satellites, one for Australia, one for Mexico, and one for RCA. You get an idea what the Earth limb looks like as you look out there. Now, not all the satellites are deployed that way. We just deployed this satellite, ERB satellite, with the arm. The arm is 50 feet long. It goes all the way down the side of the payload band. It's a pretty nice object to have. We used it on our mission to hold up the spacewalker. Now, we haven't done any spacewalks since the accident. To tell you the truth, I don't know when the next one is planned, but I believe they're thinking about doing one next year. This was 2 of the guys getting ready to go into the airlock where they put the rest of their suit on. And here you see one of the missions where this is a Palapa satellite which was damaged and didn't work properly, didn't get up to its orbit, so they were able to, with reaction control system, deorbit it to a shuttle-compatible orbit, and we sent a shuttle mission up there just to retrieve those 2 satellites. This is Joe Allen with the Manned Maneuvering Unit. And he is not connected in any way when he wears that thing to the orbiter. He's his own spacecraft when he flies that thing around. And there's a fisheye lens view of him flying around. And the satellite weighs about 3,500 pounds, and you can see that up there, as long as you're slow with it, you can maneuver the thing around with your hands. Now this is a SYNCOM satellite. It's a little bigger, weighs about 6,000 pounds, and this is Ox Van Hoften on the end of the arm. After we had retrieved that satellite and fix the problem that they had with it. Then they manually deploy it, and he was able to spin it up with his hands like this and deploy that satellite. Again, there's a unique capability of humans in space. And of course, Ox is a little more superhuman. This is a shot that I took of Jerry Ross. The guys on our mission were building space station structures. These are prototype structures. This one here we call the inverted tetrahedron. And this one is a 40-foot tower made of smaller pieces. And the two spacewalkers basically would build these things and then take them apart, build them, take them apart. And they also manipulated them to show that the human being can take a big 400-pound structure and move it around his head and really basically no problem. Now this is one of the Space Lab missions, where you've got a big laboratory the size of a small bus back in the back. After a long day of science and research, and it's nice to do a little workout. And this shot takes us back to Jack Lausma on Skylab. Notice the quality of film has changed over the years, just in 10 years. But the way we do it now is just things down in the mid-deck. There's not as much room as there was in Skylab. We have that treadmill, and then we have Gordon Fullerton here demonstrating zero-G pull-ups. And everybody knows we do military missions, but nobody knows what we do. I'm here to tell you, this is what we do on military missions. On one of the flights, we took some basic toys up from the local museum, spent a couple hours photographing various little toys that kids are familiar with so that they can see what does and doesn't work in weightlessness. Give them a little better idea of what weightlessness is all about. As you can see, the yo-yo is no big deal. Jacks are a little different though. And how about this little car around the racetrack? See, that's when the kids begin to understand about weightlessness, when they see these things. Here you see Bo Botko taking a little gyro and spinning it around, tumbling it, and then showing what happens after you spin it up. Of course, as he pushes on the thing with the little string, it wants to stay in that same attitude. The museum got a big kick out of this. They made a movie out of all these little projects that they show to kids in Houston now. Now it's time to dig into the pantry. All the food that we eat is basically kept in plastic containers. It's either dehydrated or irradiated. We don't yet have a refrigerator freezer on board the shuttle. And really we don't need one. The food that we take up there is fine. It's not what I call great, but it's adequate. And after about 3 or 4 days, you're pretty hungry. You could eat anything. The idea is you take the little container, you put 2-3 ounces of water in it, put it in the oven, and it's ready. That was Ox. Here's your M&Ms. NASA was worried about having the M's on there, so they had them all erased. But that's what they are. This is Pinky Nelson demonstrating a little fluid ball. That's coffee right there. Nice try. This is ball of orange juice, again, just floating free in the cabin. I don't know if you can see that, but there's a bubble right in the middle of it. Of course, in weightlessness, bubbles don't go up or down or anywhere. They stay right where they are. That's why we don't take Coca-Cola or any kind of fizz drinks with us, because the bubbles will stay in your stomach and you can't get rid of them. After all that fluid, you got to get rid of it. This is the bathroom. We've got these little privacy curtains on there. And that's the toilet right there. It's a zero gravity, high-tech toilet. It's got a couple of switches and dials on it. We don't have a shower like they had in the Skylab days. Skylab was a little bigger, and they had a shower that they would pull up around them. That's Bill Pogue demonstrating it. Basically, you just squirt water on you and then vacuum it off. But we do have other things. We got the shavers, and you can brush your teeth. And they'll issue you toothpaste that you can swallow, so you don't have to worry about that. We asked Gordo to demonstrate the whole toilet kit here for a film, which he said he'd be glad to do. And after all that, it's time for sleep. It wasn't real easy to sleep the first night. People were still had a lot of adrenaline going on. So this is a little later in the mission. But you basically get your bag and you just pin it up any place you want. And turn off the lights, put the shades in the windows, and hit the sack. Now what you're looking at here is the orange glow around the windows during re-entry at night. The whole vehicle is bathed in that ion sheath as it comes down through the atmosphere. Back in the Apollo days, it came down by parachute, and the ships went out and retrieved them out of the water. The space shuttle is different. It comes down and becomes an airplane. It stops becoming a space vehicle and becomes an airplane as it comes down. This is one of the landings into the Cape. We've made 5 landings at Cape Canaveral, 1 at White Sands, New Mexico, and all the rest have been at Edwards Air Force Base in California. We come down at about 17 to 19 degree glide slope, touch down at about 200 knots, which is about 220 miles an hour. And you see various landings here at the different sites. We're trying to minimize the what we call the H-dot at touchdown, the sink rate, because the landing gear are not stressed like a Navy aircraft landing gear. So we try to grease it on as best we can. Try to get somewhere around 2 feet per second sink rate at touchdown or less. There's a slow motion shot of landing at the Cape. People are into vortices like that shot. This is the view out the pilot's window. I'm sorry it's bouncing around like that, but what you do is you aim at those lights, which are about a mile short of the runway, and then down at 2,000 feet, you begin to pull the nose up, and then you aim at the runway. The outer glide slope, you're 285 knots. And the lift-to-drag ratio is so bad in this glider that you must hold 17 to 19 degree glide slope in order to hold your speed. As soon as you pull the nose up, you begin to slow down. And you touch down about 2,000 feet down the runway, then you open up that speed brake on the rudder. See how the rudder splits in half there? And that helps give you some pitching moment to keep your nose derotation under control. And after about anywhere between 8 and 13,000 feet of rollout, while the crew shuts down all the systems, and then they climb out, go get their physicals, and then go see their families. That's typical space shuttle mission. Can we get the lights, please? Now, those of you that need to go someplace or go study or whatever, feel free to do that. I'm pretty informal about these things, but there may be some of you who want to ask some questions. And if so, I'll be glad to answer them as long as you want. So, any questions? Yes, sir.
Yeah, I was wondering the status of the Space set way up in December, or is that going to be late in December?
Question is, Space Telescope, when is it scheduled? The last schedule I saw still showed it in December. And I don't know how the sunspot activity is going to play into that schedule.
They were worried about the atmosphere itself.
Yeah. Yeah, the schedule yesterday showed them still in December. Sooner the better. There's a lot of people waiting for that and have been for a long time. And it's tough keeping that mirror polished. Somebody was telling me today that it costs $1 million a month to keep that space telescope certified, ready for flight. Yes, sir.
What kind of what kind of educational backgrounds do most of the astronauts come from?
Question is, what kind of educational backgrounds do most of the astronauts have? Most of the astronauts have engineering and science degrees. We may have one or two with a math degree, but predominantly engineering and science. Most of the pilots have engineering degrees, and about half of the astronauts are pilots. The other half are engineers and scientists, and we have 6 or 7 medical doctors. We have quite a few, I'd say 4 or 5 astronomers and astrophysicists. We have 1 environmental engineer, 2 or 3 civil engineers, several mechanical engineers. Some of the mission specialists are military, non-pilot type, mostly flight test engineer backgrounds. And I think that pretty much covers most of the backgrounds. Heavy in engineering and science. We don't really have any liberal arts majors. We have a couple that started off that way. For example, Sally Ride had her bachelor's degree, I think it was in history or English. And then she got into astrophysics or something that I can't explain. Yes, sir.
Yeah, what are your feelings, and do you know of any proposals about a joint U.S.-Soviet space mission?
Question is joint U.S.-Soviet space mission. What do I feel about it, and how does NASA feel about it? We had one of those back in the Apollo-Soyuz program, and to tell you the truth, there are a lot of folks around NASA who feel like that wasn't really a two-way street. That the Soviets walked away with a lot more information about how to do space programs than we did. That they were not as open as we felt we were. Today, it seems like that environment is changing a little bit. Through the years, there's been one discipline that has tended to keep track Soviets and Americans pretty well, and that's the medical discipline. A lot of the research that the Russians have been doing in their space station, in the medical side of the house, they've had what appears to be a pretty free exchange of information with our folks. But in a lot of the other disciplines, the communications basically went away, stopped. There are a lot of folks who feel that if we're ever going to go to Mars, that we really ought to do it with the Russians. A manned mission to Mars is going to be so darn expensive that a lot of folks feel like the only way we could ever afford it is to go with them on it. So that kind of talk is going around. But I'd say that the hard feelings between the Soviets and the Americans, as far as the space people go, are getting softer. And we're going to symposiums now where cosmonauts and astronauts are invited to the same symposia, talking about space operations and crew escape things and docking and those sort of things that we weren't doing too much of that 4, 5, 6 years ago.
Do you
Yes,
ever
sir.
feel it would be advantageous for us to make a manned mission to Mars?
Do I feel like it would be advantageous for us to make a manned mission to Mars? Yeah, I sure do. I think that would be a great goal for this country to jump onto.
As opposed to like a space station, or do you think both of them are equal?
Okay, compared to a space station, well, NASA really feels that a space station is a stepping stone to a manned Mars mission, because we need to get life science questions answered on a long duration platform like space station. And we also feel that a space station is a literal stepping stone to Mars mission. You may even build your Mars vehicle on a station rather than down here. So it plays pretty heavily in all those discussions. They're not meant to be competitors. Station is part of the plan. I think any kind of long-term goal like going back to the moon, going to Mars, anything like that has much more benefit to it than just the act itself. It's just like it's like the Apollo program to the moon. The spin-offs of that program on technology, miniaturization of computers and the health industries, more than paid for the moon program, many times over. So going to the moon was expensive. It cost taxpayers $25 billion, but we got a lot of return off that. And unfortunately, in this country today, we're finding that there's a real reluctance of industry and government to think past next term or next year's bottom line or next quarter's bottom line, because we're going in short steps like that. And to think of something such a long-term goal as a Mars mission, a lot of people don't want to be bothered with it. They can't see the benefit coming out of it, but we know it would. Yes, sir.
You mentioned Crew Escape. Has NASA decided on the feasibility of the Crew Escape system for the shuttle?
Crew Escape on the shuttle. That's a pretty tough proposition because you're talking a retrofit. And remember I told you about how hard it is to make major changes to a space vehicle. Well, Crew Escape, an adequate first stage Crew Escape system is just about out of the question. And we looked real hard at it after the accident. We decided that we were going to do whatever we could for Crew Escape, but we weren't going to hold up the next launch. And so in 2.5 years, we developed a Crew Escape system that basically is nothing more than parachutes and survival equipment and a way to jettison the hatch. And that's about all we could get in there. To put any kind of a escape system that would get the crew out of the vehicle for a first stage, or when I say first stage, I'm talking those first 2 minutes of launch. Because we have solid rocket boosters that cannot be shut off or cannot be throttled back, if there's any drastic thing that happens in that first stage of flight, there's really nothing the crew can do. You can't separate from the tank, for example, and just fly the orbiter away from the stack because the structure can't handle it. The forces that you've got pulling on that structure that's attached to the orbiter are pulling too hard, and there's no way to release yourself from it. The only way to do that would be to have all the thrust stop and float, and then you could separate from the tank. And that's the way the Russians do it. The Russians have liquid boosters. So if they have a big problem at first stage, they can shut them off, and then they can separate their orbiter off of it and glide down to either a landing or a ditching. So they thought about Crew Escape at first stage, and their answer was liquid boosters. But with a solid rocket booster design, when you start those, you light the fire on those two solids, and they go for 2 minutes, and then they stop. And you're pretty much along for the ride there. The only way to get a crew out of a situation like that would be for some kind of ejection system or a capsule. It could be jettisoned off the orbiter like we used to have with Apollo and the Mercury design. But to retrofit those type systems onto the orbiter, number one, would have been a tremendous weight penalty. And we wouldn't be able to take anything to orbit. And number two, the ejection concepts, we need to carry crews of up to 7 people to do our mission. And there was no way that we could come up with a system design that would successfully eject 7 people out of a vehicle like that at first stage. And if you can't get them all out, then it's not a successful design. And that's pretty much NASA policy. Back on the 5th flight of the space shuttle, we had 2 ejection seats in the Columbia. And you may remember the first 4 flights of the shuttle were 2-person crews. And they had those 2 ejection seats that were basically borrowed from the SR-71 aircraft. They were Mach 3, 100,000-foot ejection systems. And that was their envelope. But on the fifth flight of the shuttle, we carried 4 people. And they couldn't fit, those seats were huge, and you can only get 2 of them in there. And so with 4 people in there, the pilot and the commander still sat in those ejection seats, but they had the pins in them. And they were unusable because we knew that the other 2 guys sitting in the back would not be able to get out. So that's why I say that if you're going to have an ejection system, you have to be able to get everybody out. We couldn't come up with a way of doing that. Yes, sir.
What kind of future trends do you see for industry's role in space?
Okay, the question is, what are the trends for industry's role in the future in space? You know, President Reagan and to some extent President Bush have been talking about commercialization of space and trying to get industry to have a bigger role in the launching and the satellites themselves.